Alright, so last time we talked about partial derivatives and we derived the identities relating to partial derivatives, and the reason we were interested in being able to write those identities is because there are some partial derivatives that are easy to measure in the lab. Okay, and there are some quantities that are easy to measure, easy to control in the lab, and so we need to be able to relate those to partial derivatives that we might want to know, but would be harder to measure in the lab. Okay, so the last one partial derivative that we talked about last time that would be easy to measure would be related to what is known as the isobaric expansion coefficient. And so we said that this the partial derivative in this particular case, if you wanted to know how the volume of your system changes, if you change the temperature from T1 to T2 at constant pressure, then you have to integrate partial derivative, in this case of volume with respect to temperature at constant pressure, okay, from T1 to T2. So that partial derivative happens to be equal to V times a property called alpha. And so what that means is that alpha is just 1 over V times partial derivative of V with respect to T at constant pressure. Okay, so alpha is, we say, is the fractional change in the volume per unit change in temperature at constant pressure. And so we derived alpha for an ideal gas. What was the alpha for ideal gas? So alpha for the ideal gas we derived was just equal to 1 over T. And your assignment was to derive alpha for a van der Waals gas, right? Another partial derivative that's easy to determine, you can determine it from what's called the isothermal compressibility, okay, is kappa. In some textbooks, this is given the symbol beta. Kappa sub T, I think this is what your book uses, so to emphasize that this is an isothermal quantity, so kappa or kappa sub T, okay, is negative 1 over V partial of V with respect to pressure at constant temperature. In other words, it's the fractional change in volume, okay, per unit change in pressure. But we put a negative in front because we know that if you're going to increase the pressure on your system, what happens to the volume? It shrinks, right? So this derivative right here, we know is going to be negative. And so we put a negative there in front of it just so the numbers we tabulate, when we tabulate the values for kappa, they're all just going to be positive numbers. Okay? So again, you can see that negative V times kappa, okay, volume, negative of the volume times kappa is just going to be the partial derivative of V with respect to pressure at constant temperature. All right, so how are we going to measure that in the lab? Well, temperature is easy to control, right? So you can just measure the volume at different pressures. So if you were to plot volume versus pressure, let's say you have a general curve that looks like that, what would be your kappa? So if you pick a point there, the slope of that would be equal to partial derivative of what? V with respect to P. And assuming this is an isotherm, oops, wrong graph, huh? I need a negative slope. In fact, for an ideal gas, what would this look like? It looks like that, right? So that's what an isotherm for an ideal gas would look like. So if I were to pick a point there, the slope is going to be equal to partial of V with respect to pressure at constant temperature. And so if I want to know what kappa is for an ideal gas, I just take that slope and divide that by negative V, right? So what is kappa for an ideal gas? So let's start off with PV equals nRT. Let's express V as a function of pressure. So it's nRT times 1 over P, right? So what's the partial derivative of volume with respect to pressure at constant temperature? So N, R, and T are taken as constants, right? What's the derivative of P to the negative 1? Okay, it's going to be negative P to the negative 2. So that's going to be times negative 1 over P squared, right? Okay, so that's equal to negative nRT over P times P. Why am I writing it that way? What is nRT over P? That's volume, okay? So that's volume, so that's negative volume over pressure, okay? So if that's negative volume over pressure, what would my kappa sub T be equal to? It's negative 1 over V times partial derivative of V with respect to P at constant temperature. So negative 1 over V times negative V over P. So V cancels out. It becomes simply 1 over P. So for an ideal gas, kappa sub T is just 1 over P. Okay? So to add to your homework, derive kappa for a van der Waals gas. So how do you use kappa and alpha? You can use that to calculate the change in volume when the sample is heated from T1 to T2 at constant pressure. Okay, how would I solve for this? And how do I get to use alpha in this case, or kappa? I'm looking for change in volume, right? So I want delta V. When I'm changing my temperature, so I have to do my integration from T1 to T2 at constant pressure. So what's my partial derivative going to be? Partial derivative of volume with respect to temperature at constant pressure. And so what is this? What's partial derivative of V with respect to T? That's alpha V, right? Integral from T1 to T2 of alpha V dt. Okay, what would that be for an ideal gas? Integral from T1 to T2 of, what's alpha for an ideal gas? 1 over T times V dt. Okay. And since volume is not going to be constant, you can't pull that out of the integral, right? So what's V over T? NR over P, right? So this is just going to be equal to integral from T1 to T2 of NR over P dt. So what would I get? Pressure is constant, right? N is constant, R is constant. I can pull that out of the integral. NR over P T2 minus T1, right? Which is just the same thing as nRT2 over P minus nRT1 over P, which is just V2 minus V1, okay, which is delta V. So if you know that derivative, you can just plug that derivative directly in here. You have a derivative as a function of temperature. What about, what's the change in volume? So look at this formula down here. You don't need to actually calculate your volume, right? You can figure out the change in your volume by just knowing the pressure and the temperatures. Okay, so this would have been really helpful if you have no way of measuring the volume, or if you're given a problem that doesn't tell you what the volume is, or doesn't give you enough information to calculate the volume. What about this next one right here? How would you set up the solution to this question? Calculate the volume when a sample is pressurized from P1. Change in volume when a sample is pressurized from P1 to P2 at constant temperature. What would we do this time? Delta V, what are we holding constant? Temperature. And what are we changing? Pressure. So we integrate from P1 to P2. Our integration variable is dP. What's our partial derivative going to be here? Partial derivative of volume with respect to pressure, holding what variable constant? Temperature. And we know, what did I just do? And we know that this is just negative kappa sub T times volume, right? dP from P1 to P2. And in the case of an ideal gas, what would it be? So up to here, that's generic. Okay? It doesn't have to be an ideal gas. It doesn't even have to be a gas, if you know what kappa is. But if it's an ideal gas, what would it be? P1, P2, negative. What's kappa? 1 over P V dP. Okay? Since volume is not a constant here, you can't pull it out of your integral. What's volume over pressure at constant? Is equal to what's constant here? Temperature, right? So we express it in terms of temperature and pressure. So volume is nRT over P. So P times P would be P squared. Okay, so V over P is nRT over P squared. So you can put that in there. It's going to be negative nRT. You can pull that out of the integral. Integral of dP over P squared. Okay, from P1 to P2. What is the integral of dP over P squared? Okay, so it's negative nRT, negative 1 over P. Right? So I'm going to move my negative inside, so that becomes nRT over P, evaluated from P1 to P2, which is just nRT over P1 minus nRT over P2, which is just, actually P2 minus P1, which is just V2 minus V1. Okay, so this is just another way of looking at that problem using partial derivatives. Okay, you could have solved it directly since you know this formula for volume. Okay, but the nice thing about knowing how to solve these things in terms of partial derivatives is if you're not dealing with an ideal gas, or even if you're not dealing with a gas, if you have a way of finding out what kappa is, right, then you can solve for that. How about this last question right here? Change in pressure when the sample is heated from T1 to T2 at constant volume. Oops. Let's see. What do we have there? Did I start recording? Yeah, I did record. Okay. All right, so what about this one? Change in pressure when the sample is heated from T1 to T2 at constant volume. So what am I solving for? Delta P. What am I holding constant? Volume. So delta P at constant volume equals integral. What am I changing? temperature. So integral from T1 to T2, d, what am I changing? dt, right? What's the partial derivative I need here? Partial derivative of P with respect to T at constant volume. Now, like I said, this is something you can calculate from alpha and beta and kappa T or beta, and alphas and betas are values that you can easily look up for different materials. Okay, of course this is easy to do with an ideal gas, but let's do it for the generic case in terms of alpha and beta. Okay, remember the identity we have? Okay, so let's solve for partial of P with respect to T at constant V. What two derivatives do I need to multiply it with in order to get -1? Me, you remember? What's the next term here? Partial of T with respect to volume holding pressure constant, and Pooh, what's the next derivative here? With respect to pressure holding what constant? Temperature constant. Okay, and you can see that these are things that we can easily determine from alpha and kappa. This one you can determine from alpha. What is that? This is just 1 over what derivative, Joe? Partial volume with respect to temperature holding pressure constant. Okay, and so we can see that that is what? 1 over alpha V. Okay, and this is what? We've seen this derivative earlier. John? Partial of V with respect to pressure at constant temperature. We had used our alpha, so what's the other one we have to use? And this is what? Negative kappa V. Okay. So this is negative kappa V. So partial of P with respect to T at constant volume times 1 over alpha V times negative kappa V is equal to -1. Okay? So we can solve for partial of P with respect to T at constant V. All right, let's simplify first. Volume cancels out. Okay, so that will just be equal to what? Alpha over kappa. Okay? So, we have alpha over kappa. What would that be for an ideal gas? Partial of P with respect to T at constant volume equals, what's alpha for an ideal gas? 1 over T, and what's kappa is 1 over P. So this is equal to P over T. Alright, so to solve our problem, what do we say? Delta V at constant volume, delta P, right? Delta P at constant volume, so we're doing, equals integral of changing temperature from T1 to T2, and this derivative was partial derivative of P with respect to T at constant volume. For an ideal gas, what's that derivative equal to? In general, that's going to be equal to alpha over kappa dt, right? But for an ideal gas, that's equal to P over T, right? So This is equal to integral from t1 to t2 of p over t dt. Okay? Now, since we know that volume pressure is not constant here, we can't pull that p out of the integral. We have to express that in terms of our variable t here. So what's p? nRT over v, right? So I can write this one as integral from t1 to t2 of nRT over tv dt. All right, and what happens there? T cancels out. Volume is constant, so I can pull it out. So it's just going to be nR over v, integral of dt, just t. So evaluated from t1 to t2, which is just nR t2 over v minus nR t1 over v. Of course, we know that that's the answer, right? That's p2 minus p1. Okay? So that's how you'd work that problem out. Okay. Let's take a look at closed systems. A closed system is one where the system is at material equilibrium. It's got a fixed composition. We don't want to worry about changing compositions, okay? And so we're just going to have two independent variables in this case. So we're going to limit ourselves for the time being to systems that don't have any physical or chemical changes going on, okay? So closed system, no phase changes, no chemical changes. Equilibrium. So a closed system and equilibrium would be in mechanical and thermal equilibrium. But if we change the pressure and temperature, then we can change the system, right? So we say that the state of a closed system is uniquely defined by specifying the pressure and the temperature. So we say any state function is a function of two independent variables. To define an equilibrium system, closed system and equilibrium, you need two variables, pressure and temperature. So we have two independent variables, pressure and temperature. Now, we don't have to use P and T as our independent variables. We can pick any pair of variables as our independent variables. We can use V and T or P and V. We use whatever is convenient. Okay? So whatever it is, we can easily measure or control in the situation we're dealing with, and we use that's the word. It's preferable to use variables that will give you simpler expressions, okay, mathematically. So let's say we're interested in the internal energy of a closed system. That's U. And let's say that we're going to choose temperature and volume as our independent variables for the closed system. So if I say U is a function of temperature and volume, then du, I can write du as something times dt, right, plus something times dv. Okay, so a change in U can be calculated from changes in temperature and volume. So what partial derivatives would I have here, James? First blank here. Partial of U with respect to t dt at constant. Yes. Okay, and over here, partial of U with respect to volume at constant temperature. All right. Now, the first law says that du is equal to dq plus dw, right? Now, so amount of heat and amount of work that's transferred between system and surroundings. So what if your system undergoes a reversible constant volume process? What if we limit ourselves to the situation where imagine a process where the volume is constant and it's reversible. So what's our dW in this case? The volume doesn't change. What's dV? 0. So work is 0, right? So we say then that du is just equal to dq. right? But what is dq? At constant volume. That's just CV dt, right? Heat capacity at constant volume times dt at constant volume. That's your dq. So that means what? So this is dt at constant volume. Let's rearrange this. Here, du at constant volume is equal to Cv times dt at constant volume. Okay. So if I divide both sides by dt at constant volume, what do I get? Cv, right? But since we're really dealing with two independent variables here, instead of using a full derivative, you have to use partial derivative. So we say then that the partial derivative of u with respect to t at constant v is in fact equal to Cv. So now we got something, a partial derivative involving u that we can relate to something we can easily measure in the lab, Cv. Okay? How do you measure Cv in the lab? Measure the amount of heat, divide by the temperature change, right? And then you just take the limit of that at smaller as delta T approaches 0, right? Remember the limit as if delta T is in your denominator, okay? As delta T approaches 0, okay? And that's going to be your dq, dt, right? And your dq dt at constant volume is partial of u with respect to t at constant volume. What we're saying is at constant volume, work is 0, so the only energy change is due to heat. Okay? So add that to your arsenal of partial derivatives that you can easily look up. So what do we know? What partial derivatives can we easily look up or calculate from things we can look up? Partial of u with respect to, partial of v with respect to t, which you can calculate from alpha. Partial of v with respect to pressure, which you can calculate from kappa. Partial of p with respect to t at constant volume, which you can calculate from alpha and kappa. C sub v, there's one more, partial of u with respect to t at constant volume. So for a reversible constant volume process, we say then that delta u is just Cv dt. Why? What is this? What should this derivative be if we in general, what should this derivative be? It should be from integral from t1 to t2, partial of u with respect to t at constant v. But we've already identified that this derivative is equal to Cv. Okay. Now, this is for a reversible constant volume process, but nothing in real life happens reversibly. Okay? So a reversible process, remember we say, has to do with it's an imaginary process where you make very small, infinitesimally small changes to accomplish the change. So what's the use? If the process is reversible, what's the point of knowing how to do this calculation? Well, u is a state function. Even if that's not what actually happened, okay, as long as you've identified what your initial state is, you've identified what your final state is, you can just imagine a reversible process that will take you from your initial state to your final state. If you calculate delta u for that, you get the same delta u regardless of what paths you take, right? U is a state function, it's path independent. So if you imagine a reversible process with the same initial and final state as the real process, you'll still get the delta U that you want. And that's the value of being able to develop these formulas for reversible processes. Because then when we go into the real world, we can say, okay, here's the initial state, here's the final state. Now let me imagine, how can I get from the initial state to the final state reversibly? Okay. For each of those reversible steps that I take, I just add up all the delta U's and I get the actual delta U for the real process. Okay, so here's an example, application of this. Joule expansion. Imagine you have a gas right here, okay, in a bulb, separated from another bulb which is empty. It's got a vacuum in it. by a stopcock right here. So what happens if you open this up? That's called Joule expansion. Expansion into a vacuum. Okay? Expansion of a gas into a vacuum is called Joule expansion. All right, and we're going to insulate this, so we'll do this adiabatically. So Q is 0. Or you can say even if you don't insulate it, the moment, the instant that expansion occurs, okay, heat will not have time to flow in or out. So at that instant, the process is adiabatic. So Q is 0. Since it's expanding into a vacuum, why is W 0? Remember your work is negative P external dV. Okay, so external pressure is 0. Okay, the gas pressure is not 0, but the external pressure is 0, so work is 0. Okay, so in a Joule expansion, work is 0, Q is 0. Right? Now, let's imagine, we can measure delta V for this, right? That's a change in volume. If I call this Vg and I'll call this V sub V, vacuum, what's our delta V? Whatever the volume of the second gas, and let's just call this V1, V2. Delta V will just be V2, right? Why? That's V1 plus V2, that's the final volume minus the initial volume, which is V1. Right? So you can measure delta V here. Can you measure delta T? Can you measure delta T for this experiment? Stick a thermometer in there, right? So you can measure delta T and delta V. And so if you were to take the limit of delta T over delta V as delta V approaches 0, okay, look at this. Q is 0, W is 0. What's U here? Delta U is 0. So U is constant, right? So Joule expansion is expansion at constant U. So if you take the ratio of delta T to delta V, take the limit as delta V approaches 0, remembering that this experiment is done at constant internal energy, then you get the derivative, partial derivative of T with respect to volume at constant U. So what you can measure here is called the Joule coefficient. Okay, so mu, okay, here's another derivative you can add to your list. Okay, the Joule coefficient mu is just the partial derivative of T with respect to V at constant U. Now, if you could actually do this, how would you take the limit as delta V approaches 0? If you were to do an experiment, okay, you do one experiment, you just get one value of delta T over delta V, right, for a given, let's say, the volume V2. Okay, you get a point there. How do you actually get the partial derivative? Well, how do you take the limit as delta V approaches 0? You vary your volume of your vacuum, right? So this is going to be V2. So you start off with a little tiny one, okay? And then you do a same volume, you do a little bigger volume, and so on. So you run a series of points. Okay, and how do you get the limit as delta V? This is delta V down. How do you take the limit as delta V approaches 0? This is delta V down here, right? How do you take the limit as delta V approaches 0? Well, just extrapolate. This one right here would be delta V equals 0. Okay, if you could do that. So that would allow you to calculate the Joule coefficient. Okay. Now, it turns out that the Joule coefficient, okay, for an ideal gas, let's examine this a little more closely. Let's review our identity again. Partial of t with respect to v at constant u times partial of v with respect to u at constant t times partial of u with respect to t at constant v is negative 1. We know that identity, right? So we're going to examine that identity right there. So what is this one right here? Partial of t with respect to v at constant u. What did we say that was? That's your Joule coefficient. So this is just your Joule coefficient. That's mu. Right? Partial of v with respect to u at constant t. I'm going to flip that. So what did I do? I have partial of u with respect to v at constant t instead. Okay? And I know what this derivative is. Partial of u with respect to t at constant v is cv. So this whole expression is equal to negative 1. And so you can see that if you rearrange this, you can solve for mu. So I'm just going to move my cv over to the other side and this derivative over to the other side. And so mu is just equal to negative 1 over cv times partial of u with respect to v at constant t. This expression right here, partial of u with respect to v at constant t, is known as the internal pressure, and it's your textbook gives it the symbol pi sub t. Okay, it tells you how the internal energy of a system changes when you change its volume while holding the temperature constant. All right. Now, sometime later, once we get to the second law, when we combine the first and second law, we're going to be able to derive what's called the thermodynamic equation of state. So using all these identities that relate the partial derivatives, we will be able to show that this internal pressure, okay, is just equal to this expression right here. So pi sub t, your internal pressure, okay, is equal to t times partial derivative with respect to t at constant volume minus pressure. What's the nice thing about this equation? You're expressing something, a partial derivative that involves internal energy, which is an abstract thing that we invented, right? In terms of things, tangible things that you can measure and control in the lab. Temperature. You can measure temperature. Volume, you can control volume, right? Easily. Partial of p with respect to t. What would you look up to get partial of p with respect to t? Remember? Alpha over kappa. Okay, that's just alpha over kappa. Pressure you can measure. Okay, so we can actually calculate mu from CV and this. Now, mu, if you go back here, okay, the problem with mu is for gases, it's a very small, when gases expand, okay, the temperature change typically is very, very, very small, okay? And so it would seem like mu is going to be 0 for all gases. In fact, that is true for ideal gases, as we'll show in just a little bit. The problem with real gases is that is not easy to measure. Delta T, it's very difficult to measure precisely for real gases because it's also very small. Okay, but this expression right here, if you look at this, you can actually calculate mu for your gas, whether it's ideal or not. Okay? So let's calculate mu for an ideal gas and verify that that's in fact equal to 0. Okay, what is T times D? What is pi sub T for an ideal gas? Pi sub T for an ideal gas. It's T times partial of P with respect to T over V minus P, right? This is equal to what? T times, you can go ahead and take that from PV equals nRT. What's partial of P with respect to T at constant V for an ideal gas? It's just going to be nR over V, right? Which is the same thing as alpha over kappa. That's 1 over T over 1 over P, which is the same thing as P over T. Any one of those expressions will work. Which one would you like to use? Let's use P over T. So this is alpha over kappa, right? Okay. T times, what's alpha? 1 over T. And kappa is 1 over P minus P. So this is T times P over T minus P, which gives you 0. Okay? So that means, okay, pi sub T is 0, and CV is not 0, right? You know what CV is for an ideal gas. So what does that tell you about mu? Okay, so this is 0, and this is non-zero, right? So mu must be 0. So the Joule coefficient for an ideal gas is 0. Now, real gases will have a non-zero mu, okay? But typically it's very small, it's difficult to measure, but now you don't have to worry about measuring it because you can solve it from the equation of state, from alpha and kappa. Right? So what would be mu for a van der Waals gas? If you have a van der Waals gas, okay, so what's pi sub T for van der Waals gas first? How would you do that? Let's see. What's our van der Waals equation? Van der Waals equation, P equals nRT over V minus NB minus A n squared over V squared, right? So what's partial of P with respect to T at constant V for a van der Waals gas? This whole thing is constant. So that's just going to be nR over V minus NB, right? And this whole thing is constant, so minus 0. So that's easy. So now let's do pi sub T for a van der Waals gas. That's pi sub T, internal pressure. T, partial of P with respect to T minus P, okay? At constant volume. So this is T times nR over V minus NB minus pressure, right? See what I did here is I just substituted this for that, right? So that's pi sub T. But can we simplify this? This is T times, so this is nRT over V minus NB. What's our pressure? Van der Waals gas. nRT over V minus NB minus AN squared over V squared. So that simplifies it. That gives us, this cancels out. So that just gives us positive AN squared over V squared. Okay? So that's going to be a positive number, right? What does that mean? If the gas obeys the van der Waals equation and you let it undergo a Joule expansion, what will happen to the gas? Remember, this is partial of U with respect to volume at constant temperature, right? That's the definition of pi. That's called your internal pressure. Okay, what will happen to the energy of the gas as it expands at constant temperature? Okay, let's not get confused here. Okay, so what happens to the internal energy as the volume expands? At constant temperature, this is positive. So if delta V is positive, then delta U is also going to be positive. Okay? So what does that mean? For it to expand and for temperature not to change, energy has to flow in or out? It has to flow in. Okay? So for it to expand without the temperature changing, energy has to flow in. So if you don't let energy flow in, what will happen to the temperature actually? If you did this adiabatically, its temperature is going to drop. Why will the temperature drop when a gas expands? Remember your potential energy diagram? What happens? Okay, interaction potential between two atoms, potential energy versus distance. Okay, remember that diagram? Okay, what happens when there's expansion? Let's say this is the average. What happens? Your average distance increases, right? So what happens to the kinetic energy? Decreased kinetic energy. Lower kinetic energy means, okay, in terms of temperature. Lower temperature, right? Because of attractive forces, okay? If you want those molecules to spread out more, okay, you're going to increase their average distance. You're going to lower their kinetic energy because of the attractive forces that are holding them together. Okay? Now, what happens at very high temperatures if you were to do this Joule expansion at very high temperatures? This is going to be very shallow compared to the total energy, right? So there's still going to be a drop in kinetic energy, right? But if you have essentially repulsive, if you have very high, if you can get them to a very high pressure, okay? And so if you start off with, say, let's say where the average distance was around here, okay? Then when you're expanding, okay, you'd actually be able to increase the kinetic energy first before it decreases. Okay, so depending on how much you're expanding it, you could actually get it to warm up upon expansion. Okay. All right, so what's the Joule coefficient for an ideal gas? We said that that was going to be equal to 0 because pi sub t is 0 for an ideal gas, right? And so what's the physical significance? Temperature doesn't change, internal energy doesn't change, and that's because there is no interaction between those molecules in an ideal gas, right? And reason this deviation from ideal behavior is intermolecular forces of attraction and repulsion when they're too close. So if I were to ask you for an isothermal expansion of an ideal gas, what's delta U? You should know the answer to this from before, but let's just review. What would that be? We said before that that was going to be equal to 0. And the reason for that is what integral would you have to write? Isothermal, so delta U at constant T is equal to the integral from the changing volume, right? Expansion. So from V1 to V2, what partial derivative goes here? Partial derivative of U with respect to V at constant T. And what is partial of U with respect to V at constant T? That's pi sub T, right? VV from V1 to V2. What's the integral of 0? It's a constant, right? Evaluated from V1 to V2, constant minus constant is 0. So delta U is 0. Show that U is independent of pressure for an ideal gas. Well, we have to show that partial of U with respect to P at constant T is equal to 0, right? How can we show that? Well, let's relate that to this. We know that this is 0, right? So, if you know the partial derivative with respect to pressure, with respect to volume, how can you get the partial derivative with respect to pressure? What would you need to do? V at constant T. What partial derivative goes here? Chain rule. With respect to P at constant. Okay. And what's partial of V with respect to pressure at constant temperature? Negative kappa V. Well, what is this one? Pi sub T, right? But what is pi sub T? 0 times whatever negative kappa V is, right? It doesn't matter. So what's delta H for an isothermal process for an ideal gas? Delta H is 0 because your enthalpy is not going to change. Now, consider an ideal gas. How much time do we have? It's past 9:30. We're supposed to end at 9:30. Okay. We'll do this next time then.